Yes, so this is the last video tutorial for the LAB3, task number 5, finally. Also, this video is quite short and straightforward. In this video, I want to show you how to plot and extract the FFT, which means the spectrum of a signal, okay, in your circuit. The example is very simple, but the method can be applied to extract the spectrum of any type of signal. So I'm going here, I'm LT-SPICE, so I'm opening a new window here, and I want to extract the spectrum of a square wave. So I'm going here, I have to create the square wave first. So I'm taking a voltage source, place it here, then I put the ground here, and put the label. I call it V square, and I put it here. Great. And now I want to find when I want to create this square wave. So I click Advanced, Pulse. Initial value 0, high value 5, delay time 0, my period is 1 millisecond, the T on is half of the period, which is 0.5 millisecond, rise time is 10, let's say, my rule again is 100 smaller than T on, so 5 microsecond, here also is 5 microsecond. And again, it may be also smaller, the time rise and time fall, or larger. I use 100 because again, I want that is negligible in respect of T on, okay? This is my personal rule, but you can use your own rule. The important is that it look like a square wave in the end. And that's all. So a square wave which has a frequency of 1 kilohertz, which means a one period of 1 millisecond. Now, if I'm going to perform a transient simulation here, which is what you have to do at the very beginning, is I want to see, for example, let's say 5 periods, so 5 milliseconds. Time to start saving is 0, and the timestamp I don't place anything, so that's okay. And let me move this one here down, and let me place everything vertical. So I want to extract the spectrum of this square wave here, so I click here, and this is the representation in time, of course. However, if you want to extract the spectrum of the signal, what you have to do is right click, and then here FFT. Here is already select V square. Most of the time here you don't have to change anything except in rare cases. In our course, probably we'll keep it like this for 99% of the time. So, okay, will appear a new window which will have the spectrum. Now, this representation here is very different than the representation that I show you in class also, and in class. So why is like that? The reason is because here the plot is in dB, while instead in class I put a linear axis here. So to make this one make more sense for you, although many people still use it in dB and they understand about that, in our case, in this course, we are not experts, so we are using a linear plot rather than dB. So we're going to do this linear and then okay. Oh, this one make a little more sense. It's much more similar to what I show you in the MATLAB script in the lecture, and it has many peak, many harmonics, and the harmonics start to decrease, right? However, there is still something that maybe make you wonder a little and say, but this does not make so much sense because the square wave is made by infinite harmonic because my signal is periodic, but again, here I see a triangle. It's not really a line. You remember an harmonic is represented just by a line, but this is not a line. This is a triangle, and I have many triangles here, right? So why is that? So the reason is very simple because LT-SPICE, what does is just extract the spectrum, okay, of the waveform in time that you plot. So this, so practically it takes this waveform here and it extracts the spectrum. This signal here that I show here, of course, is not a periodic square wave. I mean, at the first, here you have to be very careful because at the first sight, okay, you can say this one is a periodic square wave. But if you think about the definition of periodic square wave, a periodic square wave is a signal that has infinite period and extend to the infinite time, okay? This is, yes, is periodic, this one that I plot here, but it's not extending to infinite, okay? Because again, a periodic signal, an ideal periodic signal, is extend to infinite, okay? Is oscillating until infinite time, right? When t go to infinity. Um, but in this case, in my plot, this does not go to infinity. I just select 5 period of my square wave. So the plot that you see here, this spectrum here is actually the spectrum of 5 period of a square wave. This is the most precise definition. So what you see here is again the spectrum of only 5 period of the square wave. So when you take only 5 periods, the line, the harmonics, deform and become a triangular, okay? But so what you should think now is the following. So whatever I told you now, it means that if I plot here more period, it means that the spectrum will approach more to the ideal one with the line. Again, the spectrum I'm expecting to see here is a bunch of lines here, which each lines represent the harmonics of the signal. However, here I see triangles, and the reason is because my signal is not actually an ideal periodic signal because it's just 5 periods. And an ideal periodic signal instead is infinite periods, okay? So this spectrum here I'm plotting is just the plot of a square of 5 period of square wave. That's it. If you want a spectrum of something that look more like an ideal spectrum, okay, of a square wave, I need to increase the number of periods that I see here. So if I increase the number of periods here, then the signal I see is more, it approach to an ideal square wave, okay? But again, we will never be able to plot here an ideal square wave because we cannot plot a signal which oscillate for infinite time, right? But we can approach to it. So what I will do is now change the period, change the time here of my transient simulation and make it larger so I can see more period, okay? So here I put, for example, 50 milliseconds and I run again. So as you can see here, there are more oscillation because the time when I analyze the phenomenon is longer, right? So I can see more period. And if now I'm going, let me remove this FF, no, let me keep it maybe. Remember that the previous FFT, this is the previous FFT is called draft 7 FFT. And I'm going now to extract, why it appears the current here? I'm going to extract now the FFT of this new signal here, which is the same of the one before, but I make longer my observation window. So I extend the simulation, okay? What I'm expecting is to see a better spectrum because this one looked like more like a periodic signal because it oscillates for longer time. So FFT, P square, there it is, and then linear. As you can see, if I compare this new spectrum, okay, with the previous one, the new one has the line which are much thinner, okay, they are much smaller. You see, there is still a triangle here. You can see if I zoom in, but if I keep, you see now the zoom is the same for both picture. In the left picture, which is the previous spectrum, it looked like more a triangle. And in the new picture, in the new spectrum, when I have more period, then it looked like more line, more like harmonics, right? Of course, if I zoom in, it's still like a triangle because this square wave here I see here is not actually a real square wave, but let me put it like this so you can see better, -1. And you can see it's a square wave, but I can see more period, but it's still not an ideal periodic signal because there are not infinite period. A periodic signal has infinite period. So if I increase even more, if I observe this signal even more for longer time, let's say 100, let's say 1 second, for example, where I have many, what happened? Why did not? Okay, here. see now the simulation go from 0 to 1 second. I cannot discriminate anymore the square wave, but if I zoom it in, then I can see there is the square wave, but zoom out. But otherwise, it's too small the period to see actually the period. So now I'm going to extract the FFT of this signal here and linear. And you can see that now the harmonics look like more like a line as I was expecting. So an harmonics has to be like a line, you see. If I zoom in, of course, it looked like there is still a little triangular because again, this signal here I'm plotting is not an ideal square wave, periodic square wave. But again, this one looked more like something I would expect from the spectrum of a square wave. So, and then you have to also being able to export this plot. Again, it's very simple. Again, file, export here, and then you just save it wherever you want, and then you click OK. And I will show you then how to import this one in MATLAB and how to plot it again. But again, I want to emphasize again the fact that the longer you observe a periodic signal, okay, the more precise is the spectrum that LT-SPICE give you. Okay, this is very, very important. Okay, but now I will show you how to import the signal in LT-SPICE in MATLAB. Okay, so here I open now MATLAB and you can see I'm in the folder. I'm in the folder where I save my spectrum, which I call it spectrum squarewave.txt. And also I save in the same folder this file, which you can find in Canvas. You have to download it. And then I'm going to open this file here, and which will help me to plot the spectrum in MATLAB. So I double click here. I have to share the new window. Let me see. Okay, let me see 1 second. There's so many windows open, so I have to close a few. Here, okay. Okay, so now I have only that one open, and now I share the screen. I suppose it should be this one here. So you should be able now to see my code, the code that you find to plot the spectrum. Again, before to look about the code, let's have a look about what is inside of that file, right? So I'm going here and now share. No, this one is not. Oh yeah, I actually exported the wrong file because I exported the one in time. As you can see, indeed, when I open the how to share it now. I just opened the file that I exported, and you can see it here, and you can see there is time and v square. This is just the signal in time, right? It's not the spectrum. So I have to go back to LT-SPICE and export the correct. So okay, I finally sorry for the mistake. I now exported the correct file, the spectrum. So then what you see here is the file that I exported. So we have the frequency in the first column, and then we have the second column with the dB and the degree. Again, because you remember the spectrum as the phase, right? And also the magnitude. And in the plot that we saw before, there was only the magnitude, but you also have the phase, remember? So, and also in our case, we are mainly interested in the magnitude rather than the phase. So we are going to neglect this part here. But again, we need to remove all of these parentheses, all of dB, and all of these degree symbol, because otherwise MATLAB cannot read it, because these one are characters, not numbers. So the script is written in order to remove all of these parentheses here. So let me then stop the sharing and open the script. And then I'll share the script. So it should be appearing to you soon. And so the first part of this code is used, as you saw before, for the frequency response to remove the dB, the degree symbol, the parentheses, and so on. The only thing that you have to remember is just change this name here to the name of the file that you have. In my case, it's called Spectrum Square Wave. So I change here in Spectrum Square Wave. And that's it. So you don't have to do anything else. So the MATLAB will do the rest. As you can see here, you read the file, then you save it in one variable frac, one for the magnitude of the harmonics. Here, the only thing that you can see is that what I'm doing is this. What is doing this operation is transforming the dB into a voltage. Okay. Remember that dB is 20 logarithm of 10 of the signal. So here I have to do the inverse of that formula, which is implemented here. Again, I want a plot which has frequency in the bottom in the x-axis and the magnitude in volt in the y-axis. And remember that when you plot something in frequency, you will have maybe values very different, like 1 Hertz, 10 Hertz, but also 100 kilohertz and 1 megahertz. So in order to compress the scale, you need a semi-logarithmic, semi-log x. So you need a logarithmic x scale. And then this is just the label. So the only thing is required to you is just change this name. So you play, and then you should have the plot shown in MATLAB. I can see it here, but I have to share it with you now with the screen. So new share, and then here. So now you should see the plot that MATLAB showed me. Again, in the x-axis, you have the frequency, and the y-axis, you should have the magnitude in terms of voltage. And here is the spectrum of a square wave. We already expect the spectrum. I also showed in class. So you have many harmonics, and they decrease as soon as the frequency increase. So this is the procedure for plotting the spectrum in MATLAB. Again, remember to save it in PNG file, whatever, PDF or whatever, and then you save this picture in the answer of your, in the Word file, which contain all your answers. I think that's all. Let me go back to LT-SPICE to double check that we went through everything here. And yes, so I don't have anything else to say here. I will save this file for me. So remember always to save the file that you create in LT-SPICE. But except this, I don't have anything else. So let me write here, save it, task5 lab3 task5 spectrum. Okay, so that's all. So look about the text questions. So the question on the text, and answer them, and answer in the Word file. So this is, I think, is the last video tutorial. There is one more thing that I want to show you. Actually, a little more than one, because when we study amplifier, I have to show you how to build a circuit in LT-SPICE with amplifiers, and also I want to show you how to import the audio file here. But we can look about in another tutorial, maybe in one other lab, how to do that. For the moment is all. Remember to put all the answer of the of the lab in the Word file, and then upload the Word file in Canvas, so I can evaluate it and give you a quotient, or give you anyway some feedback about it. Okay, so thank you very much for your attention, and that's all for this video tutorial.